Just like circuits with multiple resistors can often be reduced to simpler equivalent circuits by using the rules for adding them in parallel and series, circuits containing multiple capacitors can often be reduced using similar but different rules when they are wired in parallel and series. Here we show two different capacitors connected in parallel to a battery. Since the capacitors are in parallel, they have the same voltage V across their plates, that is, the same as the voltage across the terminals of the battery. However, the capacitors contain different amounts of charge, given by Q equals CV, so that Q1 equals C1V and Q2 equals C2V. The equivalent parallel capacitance, Cp, also has the same voltage, V, across it, but its total charge is the total charge on C1 and C2, or Q1 plus Q2. We therefore write Q1 plus Q2 equals C1V plus C2V. This equals CPV. The voltages cancel, and we are left with Cp equals C1 plus C2 for the two capacitors in parallel. For multiple capacitors in parallel, we just keep adding terms so that the equivalent capacitance, Cp, is given by C1 plus C2 plus C3, etc. When capacitors are connected in series, the equivalent capacitance is different from when they are in parallel. Here we show two capacitors in series and reveal the following important fact. All capacitors in series, regardless of their capacitances, carry charges of the same magnitude, plus Q and minus Q, on their plates. The battery places a charge of plus Q on plate A of capacitor C1, and this charge induces a charge of plus Q to depart from the opposite plate, A', leaving behind a charge negative Q. The charge plus Q that leaves plate A' is deposited on plate B of capacitor C2, since these two plates are connected by a wire, where it induces a charge plus Q to move away from the opposite plate B', leaving behind a charge of negative Q. Thus, all capacitors in series contain charges of the same magnitude on their plates. Note the difference between charging capacitors in parallel and in series. When charging parallel capacitors, the battery moves a charge Q that is the sum of the charges moved from each of the capacitors. When charging parallel capacitors, the battery moves a charge Q that is the sum of the charges moved for each of the capacitors. Q equals Q1 plus Q2 plus Q3, etc. In contrast, when charging a series combination of N capacitors, the battery only moves a charge Q, not N times Q, because the charge Q passes by induction from one capacitor directly to the next one in line. The equivalent capacitance for the series connection shown here can be determined by observing that the battery voltage V is shared by the two capacitors. The voltages across C1 and C2 are V1 and V2, so that V equals V1 plus V2. Since the voltages across the capacitors are V1 equals Q divided by C1 and V2 equal Q divided by C2, we find that V equals V1 plus V2 equals Q divided by C1 plus Q divided by C2. The equivalent series capacitor, CS, has the full voltage V of the battery across it, but has the same magnitude of charge Q on its plates as did C1 and C2, so V is equal to Q divided by CS. The charge cancels, and we are left with 1 divided by CS equals 1 divided by C1 plus 1 divided by C2 for the two capacitors in series. This equation states that the reciprocal of the equivalent series capacitance is the sum of the reciprocals of the individual capacitors. We can extend this for multiple capacitors wired in series as 1 divided by CS equals 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, etc. It is possible to simplify circuits containing multiple capacitors in the same general fashion as that for resistors using these two rules for adding capacitors in series and parallel. In summary, capacitors wired in parallel have the same voltage across them. The equivalent capacitance of multiple capacitors wired in parallel is given by Cp equals C1 plus C2 plus C3, etc. Capacitors wired in series all have the same magnitude of charge on their plates. Finally, the equivalent capacitance of multiple capacitors wired in series is given by 1 divided by Cs equals 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, etc.